All right, the last talk in our event for junior researchers will be by Vikraman Choudhury from Indiana University, Bloomington, who will talk about symmetries in reversible programming from symmetric rigged groupoids to reversible programming languages. All right, go ahead.
All right, hi. I'm Vikraman, and this work was done last year when I was in Cambridge. Right now, I'm a postdoc in Glasgow, and my research is in computer science, as in like programming languages and semantics of programming languages. This work started because of my interest in reversible programming languages, which was because my advisor Amr Sabry started thinking about them, and so there's an interesting connection between reversible languages and groupoids, because you want all the programs to be able to run forwards and backwards, and that's the connection with homotopy type theory. So perhaps I can tell you some of these connections and what we proved and how this could be useful to HOT. So this work is joint work with my co-authors Jacek Karwowski and my advisor Amr. And I think Robert Rose, who is also in the audience, has been very helpful in discussions over the years when we were both at Indiana. So yeah, so I'll go ahead. So the main mathematical result that I'm presenting is the fact that the free symmetric rigged groupoid over the empty signature is equivalent to the free symmetric monoidal groupoid over the unit type. And this is equivalent to the groupoid of finite sets and bijections. So so the groupoid of finite sets and bijections in HOT is the subuniverse of finite types, where we use a predicate to just pick out only the finite types, which are equivalent to fin n. And on the left, we have a completely algebraic description of a symmetric rigged groupoid, which is like it has all the generators and relations and the coherences.
Have you switched slides? Because I'm seeing slide 1 still.
Oh. Let me get out. Is that does that show my window?
Yeah, now we can see the correct slide.
Okay, should I maybe just share my entire screen?
Well, yeah, whatever you think.
I was sharing the window. Okay. 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 Do you see the second thing? Okay.
Yeah, now it's good.
All right. Okay. So yeah. So the goal of this talk is to tell you about how we prove this equivalence between the free symmetric groupoid and the groupoid of finite sets and bijections. So on the left we have the groupoid presented as using the generators, which is like 0, 1, the tensor products and the monoidal equations. And on the right we have the groupoid with finite types and extensional functions, which are the isomorphisms between them. Okay. So why are we interested in this? So I'll give you some motivation coming from computer science. So fundamentally, computer science is about computation, and we have different models of computation. So one model of computation is, of course, like Turing machines, and which inspired like all of programming languages, trying to build total functional programming languages, such as lambda calculus, and then there are circuit models of computation. So one of the basic building blocks is boolean circuits. So for example, if I wanted to write a full adder which adds two numbers like 2 + 2 and produces 4, this circuit consumes 4 bits of input and produces 3 bits of output. So if you think about it in terms of a physical circuit which consumes electrical signals, it's actually losing 1 bit of information. Now for this circuit, of course, I mean, it's very easy. Like we just have to make sure the number of input bits and the number of output bits match. So we just pad it with a 0 on the left. And this idea is very common in quantum computing, where all the operations before you take measurements are reversible operations. So people have thought about how to build reversible models of computation where where the number of bits between the input from the input to the output is the same. Number of bits is preserved, and is it hello?
I'm a bit confused. The number of bits matches, but 1 + 3 and 2 + 2 give the same output. So is that really reversible?
Yeah. So I mean, there are different ways of producing 4. Of course, yeah. So I mean, yeah. So there are different permutations between 4 and 4, and each of that is each of those is a reversible program.
So I don't see how this is reversible. I guess I must be misunderstanding.
Okay, so the reversibility is not in the computation. I'm talking about the reversibility of the number of bits. So what this function is computing is a permutation on fin4 on the set of 4 bits. It's rearranging the bits so that we can encode the computation 2 + 2 = 4. Okay, I'll go ahead with more examples. Maybe that will clarify things. So what we want is a calculus where we can manipulate bits without changing the number of bits. Okay. So this is a language which is which has finite types. So 0, 1, and we can combine them using plus and times. And so 0 type doesn't have any values. The unit type has 1 value, and the plus has injection on the left and right, and products are tuples. And in this language, we're going to add a special kind of program types which allow us to name the isomorphisms between types. So there's an identity, and then there's a unit for the 0 and the for the plus and the times. The unit for plus is 0, and 1 is the unit for times. And there's you can swap the bits, like a + b goes to b + a times b goes to b times a, and there's associativity. And and then there's distributivity between plus and times. So a + b times c, c distributes over the times distributes over the plus, and we get all these isomorphisms. And so the language it's a bunch of combinators which can be composed. So we name these isomorphisms, and they can be composed in these 3 different ways. So sequentially using this composition, or in parallel with the functoriality of this tensor product. Okay, so so this is a language which allows you to program with type isomorphisms, and it's a first-order language where you compose them using these combinators. Okay, so what are some examples of programs that you can write in this language? We can express lots of reversible Boolean circuits. For example, so these circuits appear in quantum computing, reversible computing, and an example of such gates is like the controlled NOT gate or the Toffoli gates, which can be written in this language. So we can define a control combinator which takes a combinator, and depending on and then okay, so first it splits the 2 into 1 + 1. So 2 is encoded as 1 + 1, and this is and then using the distributivity, we distribute the times over the plus, and it applies c to the left, and it doesn't apply anything on the right, and then factors it back to 2 times a. So so for example, the NOT gate, which turns 0, 1 into 1, 0, and then we can define the controlled NOT gate, and define a controlled NOT gate, which is the 3-bit Toffoli gate. So the 3-bit Toffoli gate is universal for reversible computing, and this language can express lots of interesting. It gives a higher order language to express lots of interesting reversible Boolean circuits. Okay, so it's a programming language. It has it needs to have semantics, and the way this is usually done is by expressing the equations which tell you, like, if you run a program on a particular value, what is it going to produce. So one way of writing this is to say, given a combinator and I input this value, it's going to produce this. Okay, so we can write this down. It's a bunch of equations. Yeah. So, but abstractly, all this is doing is actually just computing a bijection. So for each combinator, it's producing a bijection or a type isomorphism. Okay. So the obvious question is, does it compute every bijection for some notion of model? Does it compute every bijection in the model, or bijection between some sets? Okay. And the other reason we think about semantics is to think about when two programs are equal. So consider these two programs, which I'm drawing as a bunch of tree transformations. So P1 and P2 both change this type A plus B plus C into C plus B plus A, but they do it in two different ways. So the first one does a tree rotation, applies swap, and then swap here. This one does three different swaps, but in 5 different steps. So, but as you can see from the figure, like, they both produce the same bijection up to, like, if you look at the inputs and the outputs. So, when we design programming languages, we think about what equations or judgmental equalities are there between these programs. So what are the equations that we need to add to decide to be able to talk about equal programs in this language? So these are the two motivating questions to figure out the denotational semantics of this language, and we'll try to answer them. So how would you design an equational theory for this language, which only has combinators? So given two combinators, C1 and C2, between the same types A and B, we write down a judgment which says C1 and C2 are equal. And just like we had combinators for producing type isomorphisms, we introduce these two combinators for producing equations between them. So there are too many of these equations, and I've written down some examples for so every combinator is equal to itself, and there's like composition, coherence of associativity, composition, naturality conditions, groupoid equations, swap, and also things like pentagon and hexagon, which come from MacLane's coherence conditions. Okay. So what is the sound and complete set of equations that these combinators produce, assuming that we are computing bijections between finite sets? Okay, so that's the other question. So if you go back to the go back to the example with P1 and P2, so we can actually indeed use the coherence conditions of a symmetric monoidal groupoid, and we can write down an equation between P1 and P2 which makes them equal, and it's basically just a hexagon and some naturality conditions. So you can visualize them using commuting diagrams. Okay, so to answer this, to answer these questions, we will turn it into a proper mathematical statement, which is, can we find the statement is, okay, so whether the groupoid of finite sets and bijections can be presented by this language. So I'm going to show that it is indeed true, but first I'm going to make a few adjustments. So this language has a lot of syntax, but equivalently, it can be presented just as the free symmetric Rig groupoid without any generators. So the free symmetric Rig groupoid, what is it? It has two symmetric monoidal structures. So one of them is 0 and the other one is 1. So 0 is the unit for the plus and 1 is the unit for the times. And then there are the monoidal coherences, the monoidal equations, lambda and rho and associativity, and lambda, rho, and associativity for plus and times both. And since it's a symmetric monoidal category, it has a swap for the plus and a swap for the times. And then there are the MacLane equations for the plus and the times, the triangle, pentagon, hexagon. And since it's symmetric, this swap satisfies swap, compose, swap is the identity. So I'm writing that as symmetry. And it's a rig, which means that the times distributes over the plus. And this is the, and so there's also a distributive condition plus some coherences, which come from the Laplace coherence conditions. So I'll denote this as pi, which is the name of the language, or f, the free symmetric groupoid on 0. Okay. So I'm going to prove this equivalence in a few steps. In the first step, I'm going to get rid of the times using the distributivity. So I'll reduce this to a language called pi plus, which is the free symmetric monoidal groupoid on one generator. So this has 0 for the unit and plus for the tensor, and the generator is the 1. And then there's lambda, rho, and alpha, the usual ones, and there's swap for the swap, and triangle, pentagon, hexagon equations just for the plus, and symmetry of the swap. Okay. So I'm going to build a functor from pi to pi plus, and the trick to building is I'll take pi plus and show by induction that it's a symmetric rig, and then use the universal property of pi to just construct the map. So so what is multiplication? Basically, just use the 0 and the 1 and the plus to repeatedly do addition, and that's how we get multiplication. So I'm just showing how to do it on the 0 cells. So define this bifunctor times on pi plus, which is 0 times y is 0, 1 times y is 1, and for the plus we do the distributive thing. And once we have that, we can construct an equivalence of symmetric groupoids between pi and pi plus. So to go from left to right, we use the map coming from the universal property. And to go from right to left, we have, I mean, it's very easy just because the left-hand side has more structure. So and then we have to prove that this is an equivalence, which relies on using the coherence conditions. Okay, so going from pi to pi plus, we have reduced the number of equations. Okay, and then we will go one more step, which is pi plus still has too many equations because the natural numbers. So the objects are almost natural numbers, but there are different ways of representing them because it could be like 0 plus 1 plus 1 or 1 plus 1 plus. So we're going to convert them into unary natural numbers. So what I'm going to write is I'm calling this pi hat, which is just the minimal prop, the product and permutations. So the objects of this are the natural numbers generated by 0 and swap, 0 and successor. And I'm going to add swap, which is going to add adjacent transpositions when you have two successors. So for every n, successor n, and successor n has a transposition. And I'm going to add a symmetry, which is swap, compose, swap is reflexivity. And I need a hexagon condition, which says that if I have 3 swaps, I can move them around. And yeah, so this has only a few equations compared to pi plus. Okay, so again, I'm going to build a functor from pi plus to pi hat. To do that, first, I'm going to show that pi hat is actually symmetric monoidal, and well, it's the minimal prop, so we have to generate all the monoidal equations by the induction principle. And well, the basic stuff is, well, associativity is how it works on natural numbers, and associativity and unit laws, and then addition is commutative. So this works out. And so how do you show that it's commutative? So there's some interesting combinatorics going on when trying to build a symmetric model structure. So one way to visualize them is to think of these trees. So just as an example, I drew the tree for the recursive case when trying to do addition of these. So you have successor of n plus m, and you want to turn it into m plus successor n. So you do an associative, a right associativity, and turn it into 1 plus m plus m. Then swap the whole tree, and then swap the leaves here, and then swap it again recursively, and this gives you the whole big swap. And this this generates the whole symmetric monoidal structure, and you can also show that Maclane's pentagon and hexagon laws hold. And not just that, and also you can go back from pi hat to pi plus, which is simply so this should be yeah, pi hat to pi plus. So you have these so pi plus has the big swaps, and we just want to produce adjacent swaps, and that just follows by turning a 1 plus x to just 1 plus 1 plus x, applying swap locally, and then turning it back. Okay, so this so if you compose these, we get an equivalence between pi and pi hat, which is a symmetric monoidal equivalence. Okay, so we've reduced to pi hat, and then the last step is to go to Ufin, which is finite sets and bijections. So Ufin is, I'm sure everyone knows the groupoid of finite sets and bijections. People have studied it very much, and so it's a one groupoid. We write it as this predicate which picks out only the finite types. Sorry, there's a typo here. So which picks out the finite types, and this is zero connected because truncated to zero, we get the natural numbers, and for every natural number, it has all the permutations on it. There is also a different way of thinking about Ufin, which is like we start from this univalent universe U, and we use a prop valued predicate, which is this thing, to pick out only the finite types, and the total space, the pi1 from the total space to U is going to reflect the equivalences. So so to talk about the identity type in Ufin, we only have to we can use the automorphisms on the finite sets. So the zero truncated structure is just the natural numbers, and it's these it's the loop space that we that encode the permutations. So now we are going to show how to characterize the loop space. So pi hat is also, so on the one hand we have pi hat, on the other hand we have Ufin. So we're going to take the group structure of the loop space, and we're going to show that this is the symmetric group. So there are many ways of presenting the symmetric group. So we want to find a complete set of generators and relations for the symmetric group. So I'm going to use the Coxeter relations, which are in Maclane's coherence proof. He also uses the Coxeter relations. So what do the Coxeter? So turning these adjacent transpositions into a word in the symmetric group. Well, this can be visualized as braid diagrams. So there are three basic building blocks for these relations. So one is cancel, which is like if I have two adjacent transpositions, I can cancel them. Then there is the if I'm swapping them like this, I can slide the wires along and I can swap them like this. And then there's the braid relation, which is, again, I can slide this wire freely from here to here, and these two things are equal. So these are the generators for the relations, and now we have to encode them into type theory so that they satisfy proper reduction, and they're directed, and I can use them to decide equality of two different words in this group. So cancel, swap, and braid. I wrote down the relations, but like we had to play around with it to make it work properly. And the goal is to take the generating set, which is list of Finan, add these relations, and produce a confluent and terminating rewriting system. So we built this rewriting system, and it's confluent, and confluent and terminating, and for every word in list of Finan, we can always use this to produce a unique word, which is reflexive transitive closure of this relation, it will go to that V. And this allows us to get a unique choice function out of it. So given any word, we can always produce normal form for this word, which is in the relation. And this Sn, and we can show that this Sn is presented basically by taking list of finite and quotienting by this relation. I have an example of like when we did P1 and P2. So P1 looks like this as a braid diagram. P2 looks like this. But after running it through the rewriting system, both of them reduce to this normal form 0, 1, 0. Okay, so okay, so we still have 2 more steps. So we need to go to a bijection of finite sets. So from this normal forms of words in the symmetric group, I'm going to show that these correspond to certain kinds of permutation codes called Lemma codes. So Lemma codes so permutation has like between fin and fin n factorial elements. So Lemma codes are a way of encoding this as just a sequence of numbers. So basically, it is Lemma 0 is computing n+1, Lemma n is computing n+1 factorial, and the idea of this number it's that it encodes the number of inversions that the permutation produces, and as it turns out, we can write this function which takes a Lemma code, embeds into a normal form for a word in Sn, and so then we get, okay, so Sn is equivalent to the image of the normal form, and this is equivalent to a Lemma code. And then the final step is to take a Lemma code and produce a bijection. Okay, I think I made a mistake in my slide here, but so given a Lemma code, you have the number of inversions, and this produces an automorphism of fin of Sn. So yeah, so there are a few different steps to this, and it's all very well written out and in the paper, but which I'll point to later. So what can we do with this? So coming back to the reversible programming language, what we can do is this gives you a normalization by evaluation procedure for this language. So we go through these steps, evaluate and code it back to the original language, and you can show that this always gives you a normal form for a certain definition of what it means to be a normal form. And using this, you can decide program equivalence and also show that the equational theory is sound and complete. I want to quickly point out that, yeah, so basically what this gives us is a, in programming languages, people care about the Curry-Howard and the Lambic correspondence between algebraic structures and programming like the simply typed lambda calculus and Cartesian closed categories. And so here it's about symmetric with groupoids and reversible programming languages. And using this equivalence of groupoids, we get these correspondences between the one combinators and the one paths and the bijections and the homotopies. And we use this stuff to prove some interesting syntactic theorems about this language, such as normalization, equivalence of two programs, and how to synthesize reversible circuits from permutations. All of this has a formalization. It was done in Hot Agda using Andrew Swan's fork of Hot Agda and Agda 2.6. It's on GitHub, and you can study the proof. And also, there's a paper in ACM at a computer science conference, which has a very detailed description of the whole thing. And I will probably also just mention a few other things, which is, okay, so this is a description of the free symmetric monodal groupoid over the unit type, but of course you can construct the free symmetric monodal groupoid over a groupoid. And I want to point out that there's some other work on constructing the free commutative monoid on a set, but this goes one dimension higher and construct the free symmetric monodal groupoid over groupoid, and it's a two monad, and one can use this work to establish all those all the higher algebraic structure of this two monad. And some other things that I've been doing with this is trying to construct generalized species of structures over groupoids, and it has very interesting Cartesian and differential structure. And perhaps this coherence for symmetric monoidal structures could be used to construct AN or EN spaces in HOT, which some of you might be interested in. I'd be happy to talk about it. Yeah, and I think with that, I'll stop.
Great, thanks very much. Okay, let's all thank Vikraman. And are there any questions?